Alhamdulillah, salatu wassalamu ala rasulillah. Dear students, assalamu alaikum wa rahmatullahi wa barakatuh. Today we will again continue our class in electromagnetics. So we will study the relation between the electric field E and the electric potential V. Okay. And also we will study, in relation to that, we will study about the Maxwell's equation. Okay. Now suppose if you take 2 points, I am taking 2 points A and another point B. Okay. The potential at A is given by VA, right? And the potential at B is given by VB, right? So the potential difference between the points A and B is given by equal to VAB equal to VB minus VA, right? That is the potential of B with respect to A. Now if you take the potential of A with respect to B, it is given by, you can have the potential of A with respect to B given by VBA equal to VA minus VB. So you can say that VAB equal to minus of VBA, right? Now you see, suppose if VAB is, so what is VAB plus VBA? From that you get that VAB plus VBA equal to 0. So what it means is, if you take a closed path, I am moving from A to B, then I am again moving back from B to A. Okay. So potential, the total potential in a closed path, okay, the total potential in a closed path is given by 0, right? Understand? Total potential in a closed path equal to 0. We can actually express this idea through electric field, because you know that V is given by integral E dot dl, right? So the potential in a closed path, you can write it like this. You have a closed path like this, right? This path is given by L. Okay. So if you are taking the potential or along a closed path, you can get it as E dot dl equal to 0. That's very important relation in electromagnetics. The total potential along a closed path is given by integral E dot here along the closed path equal to 0. Now we apply Stokes theorem that we have studied earlier. If we apply Stokes theorem to this, we can get something like this, right? Integral E dot dl equal to integral over the surface which is enclosed by the closed path into curl of E dot ds equal to 0. Understand? So from that you can get another relation which is given by del cross E equal to 0. This is the Maxwell's equation. Okay, so it means that the vector field is the electric field is a conservative vector field. That's what it means. Okay, so the electric field is a conservative vector field. Electric field is a conservative vector field. That is what it means. Okay. Now we'll move further. We have another relation also derived from the same thing, that you can write it as E equal to minus of the gradient of the potential or voltage. This is also an important relation that we can use in electromagnetics. E equal to minus gradient of V. Okay. Now, for example, you see, if you are given an electric field, example I will give you. Okay, suppose if you have an electric potential given by 10 xyz, okay, then electric field is minus of del V, right? So this is a scalar. You know, a voltage is a potential is a scalar, right? So you can write it as minus of dou, right? Minus of dou V by dou x, ax plus dou V by dou y, ay plus dou V by dou z, az, right? So you can write it as minus of dou V by dou x will give 10yz, okay? 10yz ax plus 10xz ay plus 10xy az, right? Volts per meter. Like that, you can find out the electric field once you are given the function for a voltage or potential. You can find out the electric field from the same thing. Understand? And this is how you will find out the electric field. So I will just move forward and I will give you another topic, and that's about electric dipole. We'll discuss about what is an electric dipole. Okay, we can represent a dipole as, you can say an electric dipole, it is actually 2 point charges of equal magnitude but opposite sign. Okay. separated by a small distance. That's what a dipole is. Separated by a small distance. So it will, for example, if I am doing the thing in the Cartesian coordinate system, we can represent the dipole like this. This is the y-axis. This is the x-axis, right? And you have the z-axis going on like this. Okay. Then I will have 2 point charges maybe. I will have, okay, I mean just draw the z-axis down like this. Then I will have a point charge here. Okay, I have a point charge here and another point charge here, right? And this point charge is given by minus q, and this charge is given by plus q, right? There are 2 point charges, and I have a point here P. Understand? Then I draw a line to P from these 2 point charges. Okay. And this line is given by R1. This is given by R2. And at the center you have this thing, origin. Okay. And that is given by R, right? Now, this particular angle is, this angle is given by theta. Okay. That angle is given by theta. Okay. So, in this case, if you derive the equations, I am not going into the derivations of that thing. You can see that the potential at point P. Okay. We can write the potential, electric potential V. At point P, V equal to, okay, P dot, okay, P dot vector R divided by 4 pi epsilon 0 magnitude of R cubed. This is the electric potential at point P due to an electric dipole. So here this P is actually Q into the vector D. Vector D, where this vector D is, this is the vector D. Understand? This is the vector D, where D is the vector directed from the negative charge to the positive charge. So that is the vector D. Okay. From the negative charge to the positive charge, you have the vector, small vector D. That vector defines the small distance between the positive and the negative charge. Understand? That's how. So this thing is called, you can say, this P is a vector. Okay. It is given by the charge, magnitude of the charge into, so this is actually called the dipole moment. Dipole moment. So a dipole moment exists when there are 2 equal and opposite electric charges separated by a small distance. Okay. So in the general case, for example, I'm having a coordinate system like this. I'm having a positive charge here and a negative charge here. I want to find out the electric potential at this point. I will draw the line like this. Okay, and I will have this thing. This is D. Okay, this is R1. This is R2. Okay, in the middle of the point, I will have the vector R. Okay, in that case, you can say that you have the this thing you will have, you can have another vector, this vector, sorry, I will use another color, that would be better. This vector you can call it as R dash, vector R dash, from the origin to the central point between the two equal and opposite charges, there is a vector R dash. In the general case, you can write the potential at point P is given by V equal to P dot R minus R dash divided by 4 pi epsilon 0 magnitude of R minus R dash whole cubed. So this is for if you are not having the dipole centered at the origin. In the previous case, the dipole was centered at the origin. You see the previous slide, you see. So you can see the dipole is centered at the origin, right? But if in that case, the equation is given like this: P dot R. This is for dipole centered at origin, right here. And if it is not centered at the origin, it is at any other position in space, you have the equation like this. Okay, that's how you will find out the dipole. Okay, and also the electric field due to the dipole can also be derived by finding out the negative of the gradient of this thing. So you can see that if dipole is origin, if dipole is centered at origin, you can say electric field, you can say the electric field is given by E equal to, okay, P, that is the dipole moment, divided by 4 pi epsilon 0 magnitude of R raised to 3, magnitude of R raised to 3 into 2 cos theta AR plus sin theta A theta. Okay. Thus you found out the electric field. Okay. Now we will do a simple problem. Okay, for this thing. We have an example here. You have two dipoles. Okay. dipole moments minus 5 AZ nano coulomb meter and 9 AZ nano coulomb meter are located at points 0, 0, -2 and 0, 0, 3 respectively. Okay, find the potential at the origin. Find the potential at the origin. This is the question. So you have two dipoles. One is minus 5 AZ nanocoulombs and the other is 9 AZ nanocoulombs are located. So I will just draw the diagram. We will see how it comes into being. Okay, this is the x-axis, this is the y-axis, this is the z-axis, right? One is located at the point 0, 0, -2, right? This is -1, -2. One dipole is located around this point. Okay, this is the point -2. Okay, this is plus q, this is minus q, right? And the other dipole is this. One dipole is located here, right? And the other dipole is located at the point 0, 0, 3, 1, 2, 3. Okay, so you have another dipole located here at the point 3, right? Center is the point 3, right? Now we want to find out the potential at the origin, right? We want to find out the potential at the origin. So we have to find out the potential due to dipole 1 and the potential due to dipole 2. Okay, so you can write the potential equal to V equal to P1, right, dot R1 divided by 4 pi epsilon 0 R1 cubed plus P2 dot R2 divided by 4 pi epsilon 0 R2 cubed. That's how you will find out this thing, right? Now, what is P1? You know, P1 is given by minus 5 AZ, right, into nano, it is 10 raised to minus 9, right? 10 raised to minus 9 coulombs meter, right? And you know P2 equal to 9 AZ into 10 raised to minus 9 coulombs meter, right? Understand? What is R1? R1 is the vector from the center of the first dipole to the origin, because we are asked to find out the voltage at the origin, right? So you can write it as 0, 0, 0 minus 0, 0, -2. Okay, so it will be 0, 0, that is 2, we can write it as 0, 0, 2, right? And magnitude of R1 is 2, right? Similarly, the vector R2 is given by 0, 0, 0 equal minus 0, 0, 3 equal to 0, 0, minus 3. And the magnitude of R2 is given by 3. Right? Now, you can do the calculation. And if you do the calculation, you will get it as the first term is, you can take out 1 by 4 pi epsilon common outside, right? 1 by 4 pi epsilon is 10 raised to minus 9 by 36 pi, right? You can take it outside. Then P1 dot R1, right? What is P1? That is minus 5 AZ, right? Okay, that you can write as a, you can write it as a vector, right? You can write it as 0, 0, minus 5, right? Into 10 raised to minus 9. You have to take the dot product of that with the R1. R1 is, as you can see, it is 0, 0, 2 divided by magnitude of R1 cube. That will be 2 cubed, right? Similarly, for the other case, you know P2 is given by 3, 0, 0, 3 AZ, 9 AZ, right? So you have to write it as 9 AZ is 0, 0, 9, right? 9 AZ is 0, 0, 9 into 10 raised to minus 9 again, multiplied by the vector is given by 0, 0, 3, not multiplication, that is dot product. Okay, you have to divide it by 3 cubed. Okay, so if you do the calculations, you can find that this is a dot product between minus 5 AZ. Minus 5 AZ is a dipole moment for the first thing. Minus 5 AZ I have written it as 0, 0, minus 5. I will take its dot product with the vector R1, 0, 0, minus 0, 0, 2, right? Similarly, 9 AZ for the second dipole, the dipole moment is 9 AZ. I have written it as a vector 0, 0, 9. I take the dot product with 0, 0, 3, which represents R2, right? So if you calculate it, you will find out the answer to be minus 20.25 volt. You can do the calculation by yourself, simple. So that's how you will find out the dipole moment. Okay. And with one more topic, we will stop this discussions. That's about energy density. We'll discuss about energy density in electric fields. Energy density in electric fields, right? Suppose how we will motivate this particular subject is, see, suppose in space, there is a point P1, for example. I have a point P1 here. Okay. What I do is, I try to bring a charge Q1. I try to bring a charge Q1 from infinity to this particular point. Okay, I am bringing the charge Q1 from infinity to this particular point. So, initially there are no other charges in space. Okay. So, if there is no charge in space, you don't have to do any work for moving a charge from any one point to another point. Okay. You have to do a work when you encounter another charge. When you want to move a charge through that space, you have to do work only when there is another charge in space which will exert an electric field. And in that case, you have to do work to bring another charge. Okay. Understand? Now, you have charge, the work done for moving charge Q1 is given by W1. Okay. W1 equal to 0. Right. Now, I want to move another charge Q2 to to another point P2, somewhere in the same space where P1 also is located. Okay. Now you see, we have a condition that at point P1 you have charge Q1. So if you want to move charge Q2 now, you have to do some work. Understand? Initially when you had to move Q1, there were no other charges in space, right? So you don't have to do any work. There is no work involved. But now Q1 is present at P1. So if you want to move Q2 now, you have to do some work. Okay. So what is that work? Work is given by the charge into the potential difference between the points P1 and P2. So you can write W2. You can write W2 equal to Q2. You have to do a work Q2 into V21 for moving a charge from infinity to the point P2. Right. Now after that, I want to move a third charge Q3 to a point P3. So in this case, you have two charges already present in space, Q1 and Q2. Okay. So you have to do work against the force exerted by both the charges. In that case, you can see W3 equal to, okay, Q3, you have to write Q3, okay, Q3 into V31, okay, plus Q3 into V32, okay. So you can write it as Q3 into V31 plus V32, okay. Initially, when you want to move Q1, you don't have to do any work. So W1 equal to 0. The work W1 equal to 0 because there is no charge present. But once when you have moved the charge Q1 to point P1, now if you want to move charge Q2 to the point P2, you have to do some work because already Q1 is present there. That's why W2 is equal to Q2 into V21. Charge into voltage gives the work done, right? And after some time, if you want to move Q3 to the point P3, now you see already through two charges, Q1 and Q2 are present. So you have to do work against the force exerted by both Q1 at P1 and Q2 at P2. So that work is given by Q3 V31 plus Q3 V32, right? This is how you find out the total work done in moving charges from infinity to some point. Okay, clear. Now this is a simple idea. Okay, so you have to do all this work. This particular work is stored in the system. This is a system. You have to do some work for moving P2, P3, P1 and all. P1 already the work done is 0. So all this work you are doing will be stored as energy in the whole system, which comprises of the charges Q1, Q2, Q3, etc. Right? So the work done will be stored as energy in the system because energy is neither created nor destroyed according to the conservation of energy, right? So we'll do a small example and we will wind up this particular session. Okay, you have three charges. Okay, -1 nanocoulomb. Okay, 4 nanocoulomb. Okay, and 3 nanocoulomb. They are located at 0, 0, 0, 0, 0, 1 and 1, 0, 0 respectively, right? -1 nanocoulomb at 0, 0, 0, 4 nanocoulomb at 0, 0, 1 and 3 nanocoulomb at 1, 0, 0. So So to find the energy in the system, to find out the energy in the system. Okay, you can find out the energy equal to W equal to W1 plus W2 plus W3. Okay, you know W1 equal to 0, right? Because moving minus 1 nanocoulomb, that is Q1, you don't have to do any work, right? Isn't it? You have Q1 equal to minus 1 nanocoulomb, Q2 equal to 4 nanocoulomb, Q3 equal to 3 nanocoulomb, right? So you don't have to do any work for moving the first charge, right? So the second charge, okay, now if you want to move the second charge, you have to do a work W2, that is Q2 into V21, right? V21, right? So what is V21? You know Q2 already, you know. V21 is, what is it? That is the electric potential at a point, right? The potential difference between the point P1 and P2, right? So you can write it as V21 is, what is it? What is it? V21, that will be Q1 by 4 pi epsilon 0, right? Then magnitude of, okay, you can say it's a magnitude of R12, right? Magnitude of R, magnitude of, okay, clear? Okay. So it will be given by, what is it actually? Q1 is, right? Q1 is minus 1 into 10 raised to minus 9 divided by 4 pi into 10 raised to minus 9 by 10 raised to minus 9 by 36 pi, right? Into magnitude, what is magnitude of R12? What is R12? You know, R12 equal to 0, 0, 1 minus 0, 0, 0, right? So magnitude of R12, you can find it out. This will be equal to, okay, and R12 will be equal to 0, 0, 1, 0, okay, that will be 1, isn't it? Equal to 1, okay, so you can write it as 1, okay, and similarly, you can 10 raised to minus 9, 10 raised to minus 9, that is cancelled, okay, isn't it? 10 raised to minus 9, 10 raised to minus 9 is cancelled, okay. R12 is okay, right? Isn't it? R12 is 1. Okay, it is 1 itself. That's not a problem. Then Q1, you know what it is? Minus 1 nanocoulomb, right? Okay. Then you have this thing coming, something. Okay. You can find out this thing, right? Similarly, for the, so we can find out what is W2. Similarly, W3, you know, it is Q3 into V31 plus V32, right? You know Q3 equal to 3 into 10 raised to minus 9 nanocoulomb, right? And what is V31? V31, you know, V31 is due to Q1, right? So you can write it as Q1 divided by, right, 4 pi epsilon 0 magnitude of That's it. Magnitude of R13, right? And V32 equal to Q2 divided by 4 pi epsilon 0 R 23, isn't it? So what is R13? Magnitude of R13 is magnitude of, that's it, magnitude of 100 minus 000. Okay, so it will be 1, right? So magnitude of R23 will be equal to 100 minus 001, isn't it? So it will be having a magnitude of square root 2, right? So if you substitute all these things and find out the final answer, you can find out that the total answer W equal to W1 plus W1 plus W2 plus W3. You can find out the final answer as equal to 13.37 nanojoules. That's how you will find out the total energy in the system. So with this, we will conclude this particular class. So thank you for listening. Please study all these things. Okay. Assalamu alaikum.